Okay, so our next speaker is John Greenlees, and he will continue his lectures on dualities for C-star BG.
Thank you. In the first two lectures, I approached from the spotting patterns point of view, and I explained how once you'd spotted the pattern, you could actually prove the result by relatively elementary means, but using chain complexes of KG modules and so forth. And we ended up, we started with the theorem of Benson and Carlson, which said that if you've got a cohomology ring, which is Cohen-Macaulay, then the Hilbert series satisfies a functional equation. So that was concrete sort of thing. But then that didn't apply if it wasn't Cohen-Macaulay. And so then we had a spectral sequence which gave a statement whether or not the group cohomology ring was Cohen-Macaulay. That you can get structural consequences of that even even when it isn't Cohen-Macaulay by localizing. But what I want to do now is just talk about a structural statement from which all that follows. So I'm going to remind you of the definition. This is a bit underhand. I'm going to make the definition that I made before, but then in the course of the lecture, the objects to which it applies are going to change. So we're supposed to have R, which is a ring. Previously, it's been a commutative local ring, and a field K, which is still going to be a field all of today. So that's fine. So this is a commutative ring in some sense, and this is a field. And you should think of this as a local ring. And the definition that I reminded you of already was that, well, R is supposed to be Gorenstein if it's a finite injective dimension as a module over itself, but then there were various equivalent conditions, and I'm only going to write those down. So R is Gorenstein of shift A if previously I talked about instead of writing this, I'd write X star. I said that X star was only non-zero in a single degree where it was K. But now I want to make this statement, which is an equivalence in the derived category. And apparently everyone else has said derived category without really explaining what it is, so I think I'm allowed to as well. Okay, that's the first thing. Then R has Gorenstein duality. Gorenstein duality of shift A if, well, the K cellularization of R is equivalent to R check. So Kenneth has told you a little bit about the cellularization, and so has Constanza. This is supposed to be in some, for example, model category. I find the best approximation to R in the localizing subcategory generated by K, and that's the cellularization. We will come back to it. And then R check, well, I'm not going to tell you what it is in general. In general, it's a something which needs significant discussion, but this is provided R is a K algebra. It's going to be an extra condition. R check is just supposed to be HOMS over K of R into K. So I probably also want an additional condition. So it's something like the cochains on BG or the cohomology of BG. It's a K algebra which is either entirely in degrees greater than or equal to 0 or entirely in degrees less than or equal to 0 and finite dimensional in each degree. And maybe some other conditions as well. But I mean, the conditions will be satisfied by the cochains on BG. Okay, so we've had, those are definitions we've had. So in the case of commutative ring, if that was commutative local ring, these two conditions were equivalent. That's not true in general, but at least the second condition implies the first, and I just want to explain. So note, Gordy implies Gore. Why? Because all I've got to do is to calculate, let's suppose R satisfies Gordy with shift A, then of course I can just calculate. Well, that's what we need to calculate to decide whether R is Gorenstein or not. And the very nature of cellularization is that it's the same definition indeed. Says that it factors through, map from K to R factors through the cellularization by hypothesis. We have this is the Gordy condition. And then, well, I defined R check to be K maps from R into K, so I just adjoint this over. Which of course is sigma K. Okay, so at least the second thing implies the first, and we'll come back to the reverse implication later. It'll be one of our steps. Okay, so now in this language, I am going to, well, yeah, no, I think next thing to do is to explain what sort of thing R is going to be. So to sample contexts. Sample context 1. This is more or less the one we've had. So we've got, these are going to be ring objects where the ambient category is chain complexes of abelian groups. So what do I need of my ambient category? I want it to have some sort of tensor product. It's a symmetric monoidal thing. So then R is going to be a commutative algebra object in it. So R is a commutative differential graded algebra. So it might be just a graded ring, and then it would be a commutative, graded commutative ring, and it would be commutative differential graded algebra with zero differential. So you know, it might be, as an example, it might be the integers, which is at least a familiar example, and K is still going to be a field. And we might have K was Z mod P. And so then I'm going to do some construction. I want to be able to do some constructions in this ambient category. like taking endomorphisms. So these have seen, they've come up often in slightly different contexts, but what I'm going to stick to is this notation. So E is going to be the R endomorphisms of K. And this is going to be, in a homotopy invariant sense. That is to say, I'm first of all going to replace K by a suitably projective object or bifibrant object. So this means this is actual endomorphisms of a bifibrant approximation to K, and it's another ring, but it won't be commutative. It's another ring. In the ambient category. So in our example, this is something that came up in Srikant's first talk. So I take, this has got, I can replace that by the chain complex, the projective chain complex, like this, which I'll call Z mod P, or I'll call it K underlined. So this is a little chain complex with non-zero in degree 0 and 1. And so then E, which I've written as hom R K K, actually means forms of K underlined, which, as Srikant pointed out, is 2 by 2 matrices over the integers, so with a differential. Possibly it's worth actually being completely explicit here, so let's do that. So that's got a basis with 4 elements. So these are copies of Z mod P underlined I'm drawing. E. I want to arrange them in this way so that I can say what they're doing. So what are they? So the map in question, this means the matrix 1, 0, 0, 0. This means the matrix, so this is 1. This is the matrix 0, 0, 0, 1. And then this is this matrix, which is 0, 1, 0, 0. And this is this matrix 0, 1, 0, 0. And we might as well just see what the differential does, just so we're totally explicit. Well, the differential of this is this, plus this. In other words, the differential takes this to P, 0, 0, P. And similarly, this one goes to 0, P, 0, 0, and we have to have a sign somewhere, so this one goes to 0 minus P. 0. Okay, so that's the 2 by 2 matrices with a differential. And of course, you can see, well, first of all, in general, that the homology, or as I'm going to write it, homotopy of this is calculated by X over I say equals, but I mean as a spectral sequence. But in this case, the homotopy of this is a spectral sequence which is collapsed, which is X over Z of Z mod P into Z mod P, which, and this is little exterior algebra on a generator Tor of degree -1. So Srikant said all this, but he said it in a sentence, so I thought I would expand it a little bit. So here we go. This is an example. Okay, but it's not an example which includes the example I want. So here's the example context 2. Pink and blue. Well, pink are the elements, blue are the differentials. Say it again. How am I defining them? Which? Yeah. So how do you calculate a differential of a map from one chain complex to another? So you take the sum of this differential and the map, and this differential and the map. So this one gives us that P, and this one gives us that P. Is that? Yeah, good. I'm sorry? So, yes, so let's see. This is in homological degree 1. This is in homological degree 0. This is in homological degree -1. Sorry, I didn't. So the chain complex is vertical. Yeah. Well, I think that's a very prejudiced point of view. Okay. Well, since we've got this far with this example, let me actually later on I'm going to come back to this example explicitly when we look again at another thing that Shrikant said, but we'll come back to that. Okay, example 2. Example context 2, and this is the one that we're actually going to need. So the ambient category is spectra, and well, if I want asymmetric monoidal category of spectra, I think Constanta's prefer. I mean, everyone's preferred option is orthogonal spectra, but let's say spectra. And so R is a commutative ring spectrum. I have got an example in, well, yes, let's have, the one that's going to cover it for us is cochains on X with coefficients in K. So I have to explain what I mean by that. Well, the one thing that Constance has already introduced, Eilenberg-MacLane spectra. Eilenberg-MacLane spectra, the Eilenberg-MacLane spectrum of a commutative ring is a commutative ring. So in particular, if I take K to be the Eilenberg-MacLane spectrum, of a field. So I'm going to call field K and put Eilenberg-MacLane spectrum of in brackets. So in other words, you're going to give me an algebraic field, an ordinary one, and I import it into the category of spectra as the Eilenberg-MacLane spectrum. I'm going to use the notation from commutative algebra, and hope it's not going to cause undue confusion. So this is what Constanza would say would be HK. So it represents cohomology, ordinary cohomology with coefficients in the field K. Okay, so when I've said that, then I can say what I mean by cochains. This is maps from the space. X is a topological space based, it's a topological space into the Eilenberg-MacLane spectrum. There you are, I wrote H, X. And so why is it reasonable to call that cochains on X? We note that, of course, the homotopy of maps from X into HK. This is supposed to be homotopy classes of maps from X into HK. And I just told you this represented ordinary cohomology with coefficients in K. So it is a thing whose homotopy is the cohomology of X. So it's reasonable to call it cochains on X. Well, I want a good convention for that, so thank you. I'll put it there. So this map is supposed to be unbased, but to make it into a suspension spectrum, I had a base point. Thank you. I mean, that's very important. But this is unreduced homology, so I should have put plus and reduced, and then very good. So I'm going to use this notation, cochains on X, and you won't go far wrong if you think about it as a differential graded algebra of cochains. Except the one thing, the one important thing we need is we need it to be a commutative ring so I can do some of the constructions. So it's impossible, unless K is of characteristic 0, it's impossible to make this a commutative ring in DGAs. But in ring spectra, that's fine. So this is a commutative ring. So HK is a commutative ring spectrum, and so cochains on X is 2. Because X is a space, so it has a diagonal, and HK is a ring, a commutative ring, so it's a commutative ring. Okay, and I've already implicitly declared what? Yes, this is an example, and this is a definition. I'm sorry? Yeah, so I'm giving an example of what R might be, just as I did here. And I said R might be Z. Yeah. Of course. Well, I mean, or you can do it various ways. That's one way of making the construction. So here, so where? Well, I mean, you know, if in most models of spectra, I can take a map from a space to a spectrum. That's a construction, and so you usually have this equality. Wait a moment, let me just write. So this is a theorem in you know, in various models of spectra. This is a theorem, or it's a definition, or something, and it depends on which model you're in, whether it's a theorem or. Sorry? The whole thing is a spectrum. It is a spectrum. Yeah. Yeah. It is a spectrum. It is a commutative ring spectrum. So, I mean, this was bound to be a sticky moment in my lecture, so I just postponed it to lecture 3. But what I'm hoping is everyone is now so used to seeing R around that they'll just treat it like we're working in the derived category of R modules, and that's what I'd like you to do. And it's honest, and Constanta's going to make it honest. Okay, good. Now, what about E? E is also HOMs in the ambient category of spectra, an enriched HOM in the ambient category of spectra, R modules of K into K. So that's just some non-commutative ring spectrum. But in this example, you can calculate it. So E is HOMs of a cochains on X of K into K. So this is the one place I'm going to use some topology. So there's going to be a hypothesis on X, but then there's the Eilenberg-Moore theorem says, provided the hypotheses are satisfied, this is the chains on loops on X. So what are the hypotheses? So provided either X is simply connected, that means connected and simply connected, or X is connected well, let's have connected. K is FP. K is a characteristic P. X is, I guess, yeah, P complete. And pi1 is a finite P group. Okay, so that's quite a mouthful, but let's observe. I mean, you know what simply connected, many examples satisfy that, but an example of something which satisfies the second condition, so is e.g. X is BG. Well, X is BG won't do unless G is a P group, if G is a P group. So there are plenty of P groups around. And actually, in general, as long as I take BG and I complete it at P, and I mean completion in the sense of Bausfield and Kahn, but I think it's not covered by what Constanta was saying. But in that case, it's P complete, and its fundamental group is a finite P group. You can say what it is. It's the largest P quotient of G. I1. It's G mod OPG, which is largest P quotient. And if you want to know more about the homotopy theory of BG, you should speak to Natalia, who is when she's recovered from jet lag. Okay. Good, so these are the two examples, and that's enough for me to now state the theorem. I'm going to say it again. If you're uncomfortable with these spectra, just pretend they're DGAs and you'll feel much better. Okay, here's the theorem. Oh, X is a topological space. I'm sorry? I mean, yes, it's fixed. I ask you to give me one, and we'll do that example. The one I want to use is this one. That's going to be the most important example for us. Good. So yeah. So, but I didn't say X is a topological space. And I should have said, you know, this is our main example. Well, I'm going to describe some methods for what I'm trying to. The theme is the usual one. So Gorenstein ring spectra are ubiquitous. I'm going to give a class of examples, which is going to be this class. But in fact, there are many other examples, and the methods I'm going to describe are methods which apply rather generally. mean, you'll see where we have to do some work. I mean, there was some, identifying what E was. That involved the Eilenberg-Moore theorem. In the form given by Dwyer and Shipley, or not Dwyer and then Shipley. But that's there will be input if you want to try and apply the methods I'm describing to a different commutative ring spectrum, you'll have to do some work. But nonetheless, the methods apply. Yeah. Okay. So with this in mind, so if G is a finite group, and K is a field of characteristic P, so of course we've got, I'm going to omit the coefficients. Cochains means cochains with coefficients in K. But I can always, I can include a point into BG, so there's a map down to K. The canonical map, like that. That's the one I'm going to be talking about. And so the theorem says cochains BG is Gorenstein of shift 0. And in fact, and also has Gorenstein shift, it has Gorenstein duality of shift 0. So now we know what that means. It means, well, let's say what they each mean. So this means that Homs over cochains BG, K into cochains BG is equivalent to K. And this means that, that the cellularization of cochains on BG is equivalent to our check, which is the chains, well, oh, interesting, which means that it's the chains on BG. So it was our check. So that's what that means. And finally, it follows that there is a local cohomology theorem for cohomology of BG. So we know what that means because we've spent 2 lectures talking about it. Means there's a spectral sequence like that. And I mean, I'm going to give a structural statement corresponding to that too, and it's the one which says cell K, cochains BG, is actually gamma, gamma M. So this is another point, I'm slipping in something here. I did warn you, last lecture, I gave you some definitions of the stable Koszul complex, which referred to elements. And when we get to it, I'll explain again that they apply in this context as well. So, okay, so that's the theorem I'm going to prove, and I suppose this is due to this form. Okay. Good. Okay, so what, the next thing is for me to explain the strategy of proof. And then we'll get on with the implementing the strategy. So the proof does go like this. You start from nothing, more or less, and then you get to the statement that cochains on BG is Gorenstein of shift A. And then you get to the statement cochains on BG has Gorenstein duality of shift A. And then you get to the statement cochains on, well, cohomology of BG as local cohomology theorem. And all of these steps are of some interest. So this step is relatively easy because it's just a question of interpreting this gamma in the right language. So let's just say interpret gamma m. Going from cochains BG and Gorenstein to Gorenstein duality, that's this cellular explicit model for the cellularization that Rekha explained. So this is model of cellularization. And notice that uses Morita theory, because I'm going to remind you of it again in a moment, but the model for the cellularization involves the endomorphism ring, which I'm calling E. And Rekha explained that a little bit. So how do I get from nothing to this? Well, there are various ways, but I'd like to sort of emphasize one of them. One of them is I can start by going to the fact, oh, when I say A is 0. And I suppose I should have a 0 here as well, because G is a finite group. So, so the group ring seems to be the star of this workshop, but that's as little Frobenius algebra, and it's self-injective, and so the fact that this is Gorenstein of shift 0 is obvious. So as long as G is a P group, you can take this step. So this is okay if G is a P group. You can take that step. And so you can get the fact that cochains BG is Gorenstein with very little input, as long as you've got the right framework. If it isn't a P group, you've got to take a slightly different route. So which is probably what we'll do. So it goes a bit like that. Okay, so and this step also uses Morita theory. So once I explain that, it's obvious that I have to next explain a little bit about Morita theory. So this is really just going to be saying what Rekha did again, but when I say it, I'll be working in this more general context, and I'll be using different notation. So there we are. So here we go. We've got a ring R, which might be one of our examples, and again, we've got a field K, and this time, this has got a hypothesis K is small. That is to say, small, compact, in the same sense that has been used before. So then, in fact, K cellularization of the category of left R modules is equivalent to the category of right E modules. So Rekha said this was easy, and it's so easy, I'm going to actually do it. So there's an adjoint pair, and we're just going to look at that. So we've got the adjoint pair goes between R modules and E modules. Let's start with R modules. Then this is the functor, which I'll call E, and it takes a module M to HOMS over R, K into M. So I still mean derived HOMS, and because I've got the K in the first variable, this thing is a right E module. That's the functor E. And going backwards, I have a functor T, which takes an E module X to X. Well, it was supposed to be a right E module. So I can tensor it over E with K. K by itself is a left E module, so that also makes sense. Well, why is this an R module? It's an R module because R acts as E endomorphisms on K. So R, so what acts on here? HOMS over E of K into K acts on that. And there's a homomorphism from R to that because R acts on K through E endomorphisms. Okay, so it's not an isomorphism, but I can restrict this. In fact, this is a completion, and we'll come back to it. Okay, so we've got this adjoint pair, and I just want to, explain a little bit about why it's an equivalence. Well, let's at least see why everything is happening in the derived category. Derived. Everything is derived, and I'm afraid you can't see the letter L there. I'm sorry. And you can't see the letter R here. Okay, let's at least think about this map, that the evaluation map. So if I started with M and I took E of it and then T of it and then co-unit of this adjunction, this is supposed to be HOMS over R of K to M over E to K. It's just evaluation. So I just want you to observe that, well, if I take M is K, so if M equals K, then what is this? This is E tensor over E with K going to K. So it's an equivalence. And then I want to say the class of M for which it's an equivalence is a localizing subcategory. It's obviously closed under triangles, as long as everything is well behaved. So class of M, which an equivalence is a localizing subcategory. So triangles are obvious. But then to get direct sums, I need to know that K is small, but that was a hypothesis. So direct sums here, K is small. Now this at least shows the co-unit. So hence, co-unit is an equivalence, on cell K R mod. I think going backwards, if I look at to see that the unit is an equivalence is easier. Unit must be going from X to ETX. ETX is HOMS over R of K into X tensor over E with K. And well, that's pretty clearly an equivalence if X is E, because then I get Hons over R of K into K, which is E. So equivalence for X equals E. And then again, it's localizing subcategory. For exactly the same reasons. And the localizing subcategory generated by is everything, hence all X. Okay, so I think I've more or less proved this equivalence, that this K cellularization of R modules is E modules. We wanted to go one step further, but before we go one step further, let's look at this example again. The one which is displayed. This is a 2x2 matrices example. For example, we visited. I mean the R equals Z, K equals Z mod P example. So what does the equivalence say? It says P torsion abelian groups is equivalent to modules over E, and of course E was just something whose homology was exterior on one generator of degree -1. So Srikanth pointed out that this looks a bit peculiar, because for example, this would mean that Homs over Z of Z mod P infinity, Z mod P to the infinity. So that's maps between two P torsion abelian groups should be isomorphic to their images over here. So where does Z mod P to the infinity go to? It goes to, so this is the functor E is Homs over Z of Z mod P into Z mod P to the infinity. So of course, you know what it is in the abelian category, and because Z mod P to the infinity is injective, that's what it is in general. So it is a copy of Z mod P, but with a certain action. I'll just write, let me write it like this, but I'll have to put some decoration so you know it's a special one. Over E, thank you. Okay, so this is slightly surprising because over here we've got Homs Z mod P Z infinity, Z mod P to the infinity, which of course is the p-adic integers. In particular, it's torsion free. And here we've got a group whose a module whose homology is P torsion and annihilated by P. So apparently the identity here is of infinite order. What's going on? So I kept up this diagram here so I could explain. Here in blue in the middle is P times the identity. So that's the thing that you would expect to be 0 here. Why would you think it's going to be 0? You'd think it'd be 0 because it's the image of a differential. So it is. But this is not central, so it's not an E map. That's not a full explanation, but it's the beginning of an explanation of why it's possible. Okay. So I mean the point is this little theorem has got some content even in a very classical situation. But it's not really duality, so good. So I wanted just to talk about the cellularization construction. So, so this is an additional theorem. So if K is not just small, but it's proxy small, so you remember what that means. That means that there exists a small w, which is a witness to it, so that K finitely builds W, W builds K, and of course R finitely builds W. So that's just a little mnemonic. So exists a W which is finitely built by K and builds K in return, but not finitely, and R builds W. So if K is proxy small, then the co-unit of the adjunction is cellularization. Okay, so I probably won't give you the whole proof, but we have observed that this thing over here is torsion, because this block, that's an E module. Every E module is built out of E. If this was E, I have E tensor of E with K, that's certainly torsion. So I build something else, I may take the localizing subcategory generated by E, it's everything. So this thing is K cellular. And there's a little trick to you look at the main is cellular, was obvious, and then for the other part, apply hom r k blank. Well, actually, you don't want to apply hom r k blank. You want to put hom r the witness blank, and see you get an equivalence. And of course, W equivalences, W cellular equivalences are K cellular equivalences. Okay, anyway, I'm going to make lots of use of this theorem, which I like a lot of things. This is also yeah, okay. I think the last thing, I started at 15:15. Okay, if I started, the last thing I should say in this general bit about Morita theory is about going backwards. So we've already looked at the map. Is it still here? Yeah, we've already looked at this map from R to this. I just want to point out, maybe all this is a remark. The map from R to, well, this the double centralizer is homs over E, K into K. Well, E is homs over R of K into K, which is the centralizer, and so this is a homs over R of K into K of K into K. So this is double centralizer. So this is the double centralizer map. And often the completion. So for example, e.g., e.g. in the two classes of examples I've given. So e.g. if I suppose R is commutative local ring of the classical variety. It is completion. It's M-adic completion. And if R is cochains on X, when X satisfies those conditions, either it's simply connected or connected and K is FP and pi1 is a finite P group and it's B complete, then this is also, in fact, an equivalence. Then it is an equivalence. So let me just show you that. This is cochains on X mapping to HOMs over chains on loops on X of K into K. And then this is a classical, the Rothenberg-Steenrod theorem says this is an equivalence. There's a second little bit of topology in there. Okay, so I think that's the page I got to. Three. Well, here is 4. Here is 5. Okay. Well, I mean, I suppose that the message is that in this context, the double centralizer is a completion in well-behaved. That's the message. That may be, I think that's probably a different message to the finite group. I'm not very familiar with it. I'm sorry? Yes. Okay.
But I suppose you are dealing with non-simplicity.
Well, yeah, that's exactly right. It is completion. So if the R was complete, then it would be an isomorphism. Yeah. Okay, so I think it looks as though I'm in a position to now try and describe the proof of the theorem. Just a question of where to begin. Since we've just talked about the fact that this we've got this cellularization, I'm going to describe this middle piece. I'm going to look at this first, this implication. That's for now. So this is, let's call it a proposition or a lemma or something, proposition or a 0 implies or D0 for R is cochains on BG. So the proof is, well, so what have we got? So let's suppose cochains BG is Gorenstein. Well, then we've got HOMs over R of K into R is equivalent to, it is equivalent to, well, it's going to be shift 0, but let's keep in the shift. So that's the Gorenstein condition. And then, well, that's easy to see. That's the same as HOMs over R of K into sigma A of R check. So in fact, I gave you that proof because R check, you remember, is Homs over R into K. Homs over K, R check is Homs over K of R into K. So I can just adjoint it over and see that that's obvious. So I've got this equivalent, i.e. Homs over R of K equivalent to Homs over R of K into sigma A R check. Okay, well then, but I'm doing Homs of K in, so I might as well insert a cellularization here. That's the definition of cellularization. And well, I should do the same over here. Now let's deal with the easy side first. R check is in fact already cellular because, well, if you imagine, we've got cochains on BG. This thing in our case is the chains on BG, and I'm going to just build it up from the bottom. This is a this is a direct limit of chains on BG n, the n skeleton. So each of those has got finite homology. So each of them is finitely built from K. And so when I take a homotopy colimit, it's still built from K, it's still cellular. So in fact, in fact, this thing is in fact R check. So I didn't need to do that step on this side. So we've got, so now we've got Homs over R of K of the thing we want on one side. Now we're trying to prove we're trying to prove this statement. So but now I've got Homs over R of K into this statement. This is Homs over R of K into the thing we want, cell K R to sigma A R check. So all I want to do is remove this Homs over R of K. And well, we can almost do that. Because we've got this theorem, which says that I can tensor over E with K and get this back again, as long as M was cellular. So why don't I just do that? So hence, Homs over R K into cell K, tensor over E K is equivalent to Homs over R of K into sigma A of R check tensor over E K. And by the theorem over there, by the cellularization model, this is sigma A R check because that was cellular. And the cellularization is certainly cellular. And that's what we wanted. There's one obstacle, which is that we need the equivalence I've got here, this one, to be an equivalence of E modules, to be of right E modules. As long as it's an equivalence of right E modules, then I can do this. Hence, provided the right E module structures agree, we may finish. We may finish like this. So what is, so that means that we've got to discuss the right E module structures on these things. So, but in fact, the claim now is, but we do it for time. The right E module structures, the right on K is unique. Well, so that we have now have to remember what E is. So E is chains on loops on a P-completed classifying space like that. And so what does this have? This is entirely in positive degrees, so pi star E is in positive degrees. I mean, non-negative degrees, in degrees greater than or equal to 0. And what is it in degree 0? And in degree 0, it is, well, let's actually write that as a, H0 of loops BG P completed is the group ring of pi 1 of BG completed at P. Because the loops just shifts things, and I told you one thing about BG completed at P, which was the fundamental group was a finite P group. And the only way that a finite P group can act on a field of characteristic P is trivially. So hence, action is trivial. There's a unique action of E on K. I mean, you have to make a little argument to say that because of the formal setup, it's only what happened in pi, and this is connective. It's only what happens in pi 0 that matters. But once you've done that, that's it. Okay, so I have proved that once it's Gorenstein, it has Gorenstein duality. And so maybe I can also prove so let's call this a proposition. Cochains on BG is Gorenstein of shift 0. So actually, I'll give you this proof. So the okay, so the proof is to say that I really want to give you the proof for G as a P group, so I'm going to do that. So for G a P group, this doesn't apply in general, but I want to start with something everyone will agree about. So first of all, KG is a Frobenius algebra. And hence, hence Gorenstein. All I'm saying is that Homs over KG, K into KG is K. So now I want to say, in general, I want to say that Homs over E of K into E, I want to say that it's equivalent to Homs over R of K into R. And you can do this using the associativity of the tensor product. So the idea is that you start with the fact I'm going to start with K tensor K over R and E. Well, so K tensor over KG with K, that's the definition of group homology. So this is K tensor over R. Group homology, that's R check. What's that, 5 minutes? Or is this? So I think I do have time to finish this just. But if I do K tensor over R with K, well, I now have to use the other Eilenberg-Moore theorem, which says that is E check tensor over E with K. So I'm now going to take that and apply Hom over K of E check tensor over E with K is isomorphic to Hom's K of K tensor over R check into K. So this implies this. Ooh. And now, whoops, that was into K. So now I'm going to adjoint over the E check. This Hom's over E of K into E check check. But of course, E is finite in each degree, so a natural map here is an equivalence, and similarly over here. R check check. Okay, so you agreed that KG was Gorenstein, so hence cochains BG is Gorenstein. So this only works provided E really is KG, so NB. E is generally the chains on loops on the P-completed classifying space. If G is a P group, BG is already P-complete, so loops on BG is G. Which is the group ring. But this step required that G was a P group. Okay, so I've given you a proof in the case of a P group. I'd like to give you the general proof because the general proof applies to all groups and because it applies much more generally. And actually there's some little fiddly bits in the proof that looks very simple there, but it's delicate. Okay, that's a good place to stop. Thank you.
Questions?
The Tate spectrum, yes. I don't know how to write that. Zero. Well, I mean, if this is zero, then I'm just playing for time here. Then this would be equivalent to the okay, so look, which does indeed look pretty much like K. So that looks like a great proof. Yes, from K to R. Oh. Yes, I guess that's correct. I believe it will be transfer. But, yeah, so I'm just, Neil's observation is that the Gorenstein duality in this case is equivalent to saying there are no maps into Tate. Any more questions or deep insights?
Not, let's thank the speaker again.